And the question I would like to ask you is, what does fair treatment mean to you? As I said, you don't have to give me any answer, but maybe just think about it for, well, 5 to 10 seconds. And I can see that we're currently 12 participants in this session, and even us 12 people thinking about it for 5 to 10 seconds, my wild guess would be that we came up with at least 20 to 30 unique definitions towards fairness. And that's kind of the problem that we wanted to target in our study on individuality and fairness in public health surveillance technology. So let's look at this issue from a more technical perspective. We have seen that we have many different forms of fairness from a social perspective, and similarly, we have various technical models how to translate those social perspectives into actual, let's say, statistical measures. So here are just 3 examples from the machine learning literature on how we can translate or create statistical measures that we can integrate into our machine learning algorithms. And let's look at those 3 examples from a concrete use case. So since we're talking about COVID-19 technologies here, so let's look at a contact tracing tool that should, based on certain features, predict whether a person is infected with COVID-19. And based on this AI-based predictions should send the person to self-isolation. And the big question in this design decision is how we can make this fair, how we can make this decision fair. And as I said, I have 3 examples here. So for example, let's look at the first opportunity how we could do it, or option how we could do it. And from a, let's say, more social perspective, it would be give them an equal probability for being true positive. So for being sent to self-isolation because they're actually infected with COVID-19. And now just imagine that we have certain subgroups in our population. So for example, let's look at men and women in this example and think about how they are treated in a fair way. So they should, for example, if we go for equal opportunity, so this first model, they should have the same probability for being sent to self-isolation because they're actually COVID positive. But on the one hand, this could be one notion of fairness. On the other hand, maybe more men are sent to self-isolation, although they don't have COVID in this case. So this could be seen as unfair. For this, we could use a second approach. So also considering the false positives, which would more be equalized odds. So this would account for the equal probabilities for being true positives and false positives. But in that case, maybe less women are sent to self-isolation in general. So we don't look at the negative outcome here, meaning that people that are not sent to self-isolation. If we want to also account for the negative outcome, we would need to implement the statistical parity model. So basically, what I want to show you with that is that there are many, many different perceptions of fairness from a social perspective. And at the same time, since we don't know what is the most fair from a more social perspective, what is actually the most fair from a technical perspective, that's even a more challenging, well, problem. So why is that especially important now? Now meaning during the pandemic. One reason for that is that ethical concerns related to fairness have quickly spread with the virus. So these are just a few examples from the news. For example, first thing that happened was self-isolation. So China was one of the first countries that imposed self-isolation regulations. And a big question here could be, is this fair? On the one hand, to self-isolate people in general, but also on which criteria can you send them to self-isolation? For that, contact tracing apps could be implemented so that we have more criteria and make this decision to send someone to self-isolation more fair. But also with more technology, we have even more fairness issues considering are those tools, for example, mandatory. As you can see here, India and China decided to make those tools mandatory, but also given that certain devices are needed for contact tracing tools, and maybe not everyone has access to these devices. A third example is then when vaccination was developed, so vaccines were developed. And of course, that led to the question of how should we distribute these vaccines? And here we even get closer to AI and also get closer to the problem that we've seen before, that it is very hard to judge which fairness approach is the best. So And here we have an example of the US developing an AI-based algorithm to decide vaccination distributions. And here, different states of the US took different approaches. So for example, Oregon has prioritized teachers over the elderly to help schools and businesses reopen. This could be seen as fair, but you could also argue that it's more important to help the elderly. Both seems some way plausible. And then a last example that, at least here in Germany, is still very up to date, and that's the question on vaccination status. So can we treat people differently based on whether they're vaccinated or not? Is this the criteria that should flow into the decision, and is that fair? And exactly this question of whether we should include more criteria and such decisions is the challenge that we try to target with our study. Explicitly, we studied the impact of individuality, so that means including more personal criteria in the decision. And we studied the relationship between individuality and three main concepts, namely fairness perceptions, perceptions of data privacy, and perceptions of the overall user satisfaction with such an application. For that, we developed a survey and studied public, let's say, an action enforcing public health surveillance tool, which is a contact tracing app. And the initial setting was a contact tracing app that collects information. Well, that's more or less standard. That's what the contact tracing apps always did. But in our case, we theoretically designed it in a way to include even more characteristics, so collect even more data to identify the risk of spreading the virus a person poses to others. So not only the person for the risk for the person himself, but also the risk that the person spreads to others. So for example, the number of contacts that this person needs. And from that, we identified two different cases, and those two cases more or less reflect two opposite approaches that a developer could take in the design of such apps. On the one hand, we have case one, which is it's more personalized, so more individualized, because it makes use of this information collected in the decision of sending someone to self-isolation. So for example, when you look at the risk of spreading the virus a person poses to others, so this would mean practically if a person comes into contact with many people on a regular basis, this person would be asked earlier by the app to self-isolate than a person that rather stays at home. So this is more individual criteria in the decision. Case two, so here on the right side, the app does not make use of the information in a decision, but just simply bases the decision on the number of exposures, so just as regular contact tracing apps. And from that, we ask the question, which one is fairer and which one do you prefer overall? So to study our three main concepts. And our results, which I thought were very interesting because they showed that the high individuality approach, so case one, was significantly here in a statistical sense, significantly rated as fairer and better overall. So when we look at our three main concepts, high individuality approach was seen as fairer. It was also seen as more data privacy intrusive, which makes sense because it does use more data. But interestingly, in the end, it was rated as overall better. So although there were negative effects from data privacy, the positive effects from the perceived fairness improvement still led to being perceived as better overall. And from that, we wanted to conclude three major conclusions. So first one is we should strike a balance between individuality and data privacy. That's interestingly something that Christian Gutman also this morning in our AI for Health panel mentioned, that we have this balance between, or this trade-off between data privacy and fairness or individuality, and we should balance both of them. Second is, or especially because of that also, we found that fairness perception strongly correlated with the overall user satisfaction. So this even highlights more that we definitely need to strike this balance between individuality and data privacy. And third conclusion, when we link that back to our fairness machine learning models that we've seen at the start of the presentations, there's a recommendation that the developers should consider this balance between data privacy and individuality in the design of such public health surveillance tools, and could consider using more approaches that allow for more individualized treatment. One last remark I have to that is, I said our results are significant, but we also identified that our effects were rather small. So in the end, that points towards that our approach, so the risk level, is among those parameters that are seen as very individual. But on the other hand, there are probably more parameters that flow into seeing something as very individualized. So our suggestion for future work would be to search for those parameters and see which parameters are seen even more as individual and can help kind of making this effect even stronger. With that, I would like to thank you. And I also think that I went a bit over time, so I'm sorry for that. But thank you for your attention, and I'm open for questions.
Thank you very much, Ellen. And no, you went 10 seconds over time. So really good performance here. All right, if anyone has questions, please feel free to send them in the chat. And if any of the panel persons here have questions, please feel free to raise your hand or just jump in right now. No questions, no comments? All right, then. I have a comment. My comment is that this was a really interesting study. And my question is, what would be follow-up studies to specify more precisely? You were saying you had small effects. So, oops. Okay, yeah, you were saying you had small effects. What would be the follow-up studies to see if those effects maybe in different contexts or maybe in different situations might be bigger?
I think I had some internet connection issue. I didn't hear, was that a question to me? I'm sorry. It
was a question, don't worry at all. Really summing up the question, what would be the follow-up studies?
So particularly, we haven't planned any follow-up studies, but as I said, I think it could be interesting to see which kind of parameters are needed to see such an application as more individualized. We just took one approach and we explicitly tried to choose one approach that is not that obvious. Because if you, for example, say, well, let's look at the parameter, is this person male or female? Well, obviously those two people should be treated based on their individual parameters, because being treated or being discriminated because of male or female is not very, very nice. So that's something that you should definitely avoid. But that's why we took an approach that is not very clear from the first start, and rather is based on personal notions, if you rather prefer to be more individualized in terms of risk level or less. So to sum up, this could be an approach for further research to look at the different parameters that are also seen as individualized, and not only at this one parameter that we looked at.
Great, thank you very much. If there is no more question for now, I would offer that we keep going with the presentations. And if anyone wants to reach out to Ellen, you can find her email address quite easily on the IEAI website, or you can add it in the chat. Probably.
Thanks.
Dirk and Georg, do you want to go next? Yes?
We can. Let me just get the slides on.
Of course, take your time.
Okay, you should be able to see the slides now. We looked at the development of AI models, in particular with the COVID pandemic in mind, and to do it get the parameters right, the criteria to develop an ethically sound AI model. So what we've done is start off with the ethical basis. And I often refer to ethics as a soft law approach because it's not regulated, but it's a starting point and it's a way of providing a lens through which you look at the development of the system. And in the process, we defined certain things we have to look at: socio-ethical considerations, critical elements or principles of a legal framework, and how that would impact on the design of a machine learning model. And to do that, we had to work very closely in the team, iteratively, back and forth, interacting with each other, but starting off from the ethical perspective. And as I indicated, ethics, different ethical theories can be used as different lenses to look at the development of such an ethical legal framework. But having said that, the ethical approach also implies that the AI model should be seen as an agent, meaning that there's some degree of autonomy and interactivity and adaptability in that model because it represents something. And in our case, the agent is a learning agent. So we develop a statistical model, machine learning model that learns and could make some predictions, to put it very simple. We also said that the ethical approach cannot be a once-off exercise that you do before you start with the development. It applies to the whole AI lifecycle. And an important tool to do that properly is to make use of user stories. For example, we said to fight the pandemic. You could imagine a user being a government official saying, I would like to predict the risk that an individual would be infected by the coronavirus in a particular setting at a particular point in time. And by bringing in those factors, one could build that user story in developing our model. Looking at the legal framework, currently there's the furthest development is the new proposed AI law in the European Union. So we had to look at what is in process, not what is regulated already. And learning from the international experience, we decided that the key legal factors or principles to incorporate in our design are transparency, accountability, dignity. You mentioned fairness in the previous presentation, and equality we grouped together, privacy and data governance, and then perhaps issues like human autonomy and oversight. But again, this is something that's not a tick box and a once-off exercise. It needs to be systematic. It applies to the whole life cycle of AI, and it starts with the acquisition of data. And already there, you need to look at how the different legal principles have an impact on how data is acquired. In our case, as you will see a bit later, we use simulated data. Then apply the legal principles also to the design of the AI, which means that you need an iterative process interacting in a multidisciplinary way in a team. And it was clear that working in such an interdisciplinary manner is crucial for a good usable end product, not only in the scientific setting, but also in real life. And then the next phase of applying the AI model, and lastly, looking at the impact of the model. We have to take into account the different legal principles. You will see that some of these legal principles, they don't have an equal weight eventually in the design of the model. Some of them, in particular, privacy and explainability or interpretability, we have accommodated reasonably well in our model. And one could argue based on that it also strengthens accountability, but I leave it there for the moment. The point is that you have a series of factors to consider in the whole design process and how you develop and implement and test the model. And I think at this point in time, I would like to hand over to my colleague Jörg Gro, who will share some ideas, thoughts about the technical part of it. Georg, I'm happy to run with the slides further.
Yes.
You just indicate when I need to move.
Yes, perfect. Thanks, Dirk. So what we did, as Dirk pointed out, it's very hard to get real data, right? So that's why we opted for a simulation-based approach, which means that the ground truth at all levels of filtering is at our hands, right? And we made actually 2 simulations, right? So the whole technical part was done in a series of more than 10 master's theses and also some bachelor students that work closely over this year. So there's a whole body of work. So each one that's interested in the ethical, legal and user story part. So each of these students put up these glasses to discuss that within her thesis, right? So we made actually 2 simulations. The first one was based on explicit frameworks, but turned out to be a bit unwieldy. So the second one was more completely handwritten. And of course, the basic building block around which these simulations were created is the encounter, right? And with the encounters, obviously comes also a long-term social network, or there is an influence between that. And with the encounters comes the disease spread, right? So you encounter people in buses, at work, wherever, right? So we had several screws to turn. And next slide, please. The interesting thing now is to say, well, what can be done machine learning wise? So all of our students took part in the simulation programming, as well as in the machine learning evaluation, as well as in the ethical analysis. So it's clear that there's a state at time t, which we can use for prediction at t+1 in that time series sense. And then there's an estimated state from which, and there's an implication by measuring, of course, right? So measuring is the way that one point where the information gets inserted into the system, right? So this is a couple of students did stuff with a more social network perspective, right? So there was one particularly successful algorithm based on PageRank, which had very good results, right? But next slide, please. What we also did was to take a location-based as well as a activity-based approach, right? So location-based is pretty accessible, I think, right? So we want to know how the risk kind of depends on locations, right? So certain areas, certain socio-spatial communities and stuff like this, with obvious ethical implications, right? But it's also not only ethical, it's also interesting from a statistical point of view, because the more fine-grained you get, the less data you will have, right? And so this is one part. What I find very interesting, and next slide, please, is the activity-based point of view, because there has been in Germany, of course, and I think throughout Europe, a large discussion on the restrictions due to the COVID pandemic, right? As in, we need to close down the clubs, we need to do this and this. So we tried to come up in several of the students' theses and our own work with the PhD students with this activity point of view, yeah? And the interesting thing is, of course, you have a relation to spatiotemporal, because not every activity is as risky as in that part of the world as in the other part of the world, right? And another big problem here is, of course, what constitutes a activity, right? So there is an ontological structure that also needs to be agreed upon, and ethically in terms of who is going to collect which data. And our point of view is not so much on the individual, as Ellen said, right? So do you take into account all the features for sending someone in quarantine? Our perspective was always more, what can we provide as information services to the individual as well as to the government, while there is a collection and then the model just integrates it. So the traces should not be traceable from the data to the individual, but more the inflow to the model and then out to the recipients, right? And since there's not a lot more time, just a couple of key findings. So what I found really interesting is that whatever models we did, and we did quite a few, if you pose detailed questions, you need almost complete compliance and almost complete data to be successful enough to bring a real added value, right? So may that be activity-based or spatiotemporal resolutions of risk and risk prediction for the individual or for the whole activity. It was always the case that we needed a lot of adherence and compliance, which is another interesting ethical question, right? Because performance must relate to the ethical, the data input, right? If you put a lot of data in, but you don't get a lot of performance out, it's pretty useless, right? But we see here, you need a lot of data to get these detailed things in all of the experiments. So yeah, with that, I would like to conclude, right? Thanks.
All right, thank you very much to the both of you. That was extremely interesting. If anyone has a question, you can write it down in the chat. Okay, I have a question. I hope I did not miss this at the beginning, and from someone not on the technical side, what is the downside of simulated data? Where might it be biased in certain directions, etc.?
Mm-hmm. Well, obviously the simulations are not reality, right? But on the other hand, if you try to get data on a scale and quality that is on par with the simulation, you'll be having a hard time. So we tried that for South Africa. And there is also data sets from the Paris region and so on. But I think as long as we stay within the course corridors of truth, what is more interesting is this screw approach, right? If we turn that kind of compliance rate up or down, what will be the resulting quality issues? And I think scientifically, if we stay in that truth corridor, more or less, right? I think it's a credible result, because we're not actually interested in the performances, but how the performance changes with certain key screws that we turn, right? And that was always our perspective. There is a bias, yes, there might be a bias, but if it's within the truth corridor, I think it's.
Okay, thank you. We have the time for another question. Is anyone in the panel willing to ask one, or I have another one? I can go with the other one. All right, great. So the next question is the challenges of interdisciplinarity, because obviously you've been working from also distance and distance in the field. How did that go?
I'll try that one. I think it actually went very well. And I guess it depends on how you set the basis to work from. If you find common ground right at the beginning and set the goals clearly, the team finds their feet and can work together. We decided to have weekly team meetings on Zoom, and that helped a lot. And obviously, I think for the machine learning students in Munich, it was a bit easier to have more frequent meetings as part of their studies as well. But I think that was in the nature of the project that should happen. A few from the Cape Town Stellenbosch area, we could also interact more regularly. But as a whole combined team, we had good synergies, and we structured the project in that way that we could learn from each other and add value to the whole development process of the research and the end results that we've seen. So I wouldn't say that there were serious challenges, except the fact that COVID prevented us from meeting each other physically. But for the rest, I think we coped well.
Great, thank you very much. We're always happy to hear a success story like this one, of course. All right, so I will now present my topic, and please, Ellen, be the time police. Thank you. Can you see my slides? Yes, sorry, I didn't. Yeah, oh, good. Okay, great. So what I'm going to present today is a research that we've been doing at the Institute over the past year on cultural and governmental factors that have impacted technology acceptance in times of crisis. That was a big question to ask because we've seen that in different countries, different types of populations, different types of technologies have been implemented and accepted. And so the big question was why? So our first approach back in end of 2020 was to see that political openness was actually a big factor. So political openness can be considered a level of democracy. So the highest a country has a political openness, the more high level the democracy really. So you can see on the table on the left, that's a table we did last year. That high level in democracies, countries tend to have less intrusive technology. So that was interesting for us to also see the opposite happen, that low level of political openness would usually be linked to intrusive technology. This is a conjecture. So this was a good start, but this is not everything. We decided to look more specifically into tracing apps because they were really broadly spread at that time. And there were a big discussion in a lot of different countries. So that will be the technology that I'm building this presentation on today. Ooh, there we go, sorry. Here is a graph of political openness and personal data, the acceptability for populations to have their personal data seen or taken by their governments. So this links to intrusive technologies. Again, this graph, I am really sorry, the name of the countries are not here, but on the extreme left, this is China, and on the extreme right, this would be Norway. And in the middle, it's the countries that you have seen in the previous table. And you can see that there is definitely an effect here that kept going. It was not just prior to the pandemic and at the beginning of it, but this is an acceptance by the population. So at this point, yeah, we were pretty sure that political openness, intrusive technology were factors, but that's not everything. That cannot be everything. We then looked into trust in governments, but also trust in technology itself. When it comes to trust in governments in times of crisis, there's something interesting happening. This is called the crisis effect. Populations have a tendency to trust their governments more at the beginning and less after. And this is something I think we can see in a lot of countries happening at the moment. But to build this trust, you need for the government to be transparent, responsive, efficient, and fair. Fairness is a topic that keeps coming up, right? Fair. So trust is not static. During the pandemic, we would expect populations to trust their government more. And was there a difference between populations? Probably, but at this point, that was not really the question. And we saw that this trust impacted the other pandemic or epidemic situation, and it helped governments to go through different epidemics. Ebola is a really good example of that. So here you can see a quote from from a research by Ryan and collaborators on the Ebola outbreak, showing that local responders employed varied technologies of trust, openness, accountability, and reflexibility to build confidence in the measures implemented. So can we see that with technologies themselves, right? That's our question. We know it works with governments, we know it works, it works with governments and with their implementation of new regulations. So does that work if governments propose new technologies, such as in the case of the tracing apps? We added one factor to this, the culture and the past experience, which actually in this context are similar. Because yes, of course, as we said, governments and political openness have an impact, but it's not all. You could see that some countries had past experience with epidemic or other terrible things, natural disasters, and they would actually have a bigger tendency to follow what their government were proposing, including the implementation of technologies. I will show you some practical examples right after. So past experience seemed to be a big factor, have a really big importance. And that's where the loose culture, tight culture theory comes in. Loose cultures are basically heterogeneous social groups whose diverse members tend to value originality, risk-taking, and a flexible adherence to collective norms of their culture or group. Simple words, individualism. Those are cultures that will have a tendency to be individualist and not follow the group as much. Tight cultures are the opposite. Those cultures, the group comes first, they will have a lot of shared things. So here you have example of language, social custom, religions, etc. Well, it goes further than that. It tends towards a rigid adherence to the collective norms of their group. Rigid adherence, which means if a technology is proposed by a trusted source, such as a government, to fight a pandemic, and there is a past experience showing that this government is actually good at dealing with that kind of things, those tight culture would have a higher tendency to follow the government and therefore adopt the technology. It's a lot, so I have a pretty figure to show you right after that, just to put everything in place. An important quote that I still wanted to have in here is that tight cultures tend to have had a lot of threat in their histories from mother natures. I mentioned that disasters, famines, pathogens, outbreaks, and non-natural threats such as invasion of their territories. I'm pretty sure that reading that list, you can picture a lot of different countries in your brain. And those countries probably did better with COVID because statistically they did. Tighter culture dealt better with COVID in general. So here it is. It is that simple or that complicated. That is our first conclusion, our main conclusion. Technology acceptance in this context was impacted by political openness, which is part of the global culture, if you can say, cultural tightness and looseness, and past experience. If a government dealt with this really well in the past, populations would have a higher tendency to follow them. This can be, of course, put in a bigger framework, such as the technology acceptance model, but because of the length of this presentation, I didn't want to get in there, but this is considered into the technology acceptance model. So now the examples. I'm not sure how much time I have left, but I will try and get into as many as possible. So the ones that are extremely interesting, as you can see on the left up, so tight and high voice and accountability. Those ones, like Norway, for example, would be extremely democratic countries that still have a high tightness. Therefore, we would expect them to accept the technology. And Norway was a great example. They did accept the technology, and the reasons they did were usually social norm. So that fully followed our theory. Iceland, tight, moderate tight, which means it's not like Norway, Malta, but still high enough to be on that side of the table. and still really democratic. Yes, you can see, so you can see that Iceland was extremely good. There is 3 stars near that name, which means that there has been a really big uptake considering of the tracing app. And on the other hand, if you go to low voice and accountability, you will find Saudi Arabia, China. Those are tight countries, but with, I'm sorry, am I over time? Not yet. Okay, 5 more seconds. And so yeah, Saudi Arabia and China are low in democracy, if we can say that, voice and accountability, but they are super tight. And actually they did accept some really intrusive technologies, because also culturally they already had some. So they just kept following what they already had, and that's interesting as well. If you want to know more about this, there is a research brief that has been published on the IEAI website that paints a bit better every country's example. But that was to give you the global idea. Thank you. Do you have any questions?
I do have a question to you. You talked about how past, so first of all, thank you for your presentation. Of course, it was very, very interesting. And what I saw is that past experience mattered. So past experience with pandemics matters for the acceptance of the technology. When you talked to your case study partners, did you also figure out whether it not only mattered for the acceptance of the technology, but also in general with coping with the pandemic in the end? So did you see that, for example, African countries that maybe struggled with the Ebola virus before, did you see that they also, dealt better with the COVID pandemic? Yes,
definitely. So we had discussions, experts interview with different countries, and as you say, a few countries in Africa were actually part of this, Rwanda in particular. And it was really interesting to see that definitely the Rwandan experts' point of view regarding the pandemic were really more chill, excuse my language, but the ones that we have here in Europe, when you have Ebola running around or HIV that is being so omnipresent, COVID seemed to be less of a big deal, even though still a big deal, right? And it's interesting because the technologies developed in Rwanda or implemented in Rwanda were extremely surprising, and I'm not sure that countries like Germany would have accepted them. So the tightness of Rwanda plus their past experience, which go together, right, and all that actually played a big role in accepting new technologies for them, for sure, and dealing with the pandemic.
Okay, thank you.
If there is no more question or comments, I think that we would be right on time for Katarina's presentation.
All right, thank you, Oksana, for your presentation and for your introduction. I will then share my screen. I think you can all see it now, right? Okay, so today I will be presenting some findings of this analysis that we propose for the European Commission repository on deployable artificial intelligence and robotic solutions that could help face the COVID-19 crisis. I will briefly present some findings that are more discussed or discussed in detail in this paper that is currently under review. So starting by the repository and this initiative from the European Commission to launch a call for ideas to collect AI and robotic solutions that could help in the response to COVID-19 pandemic. In the answer to this call, countries and organizations from private industry and research institutions participated and added ideas to these two repositories. So 2 repositories were launched, the Solutions Repository and the Initiative Repository. And in the aftermath, the European Commission launched also to funding opportunities to further develop some of the solutions within these two repositories. So for this analysis, we decided to focus on the solutions repository that was public. Both repositories are publicly available online, and the specific one was lastly updated in May 2020. And this is how it looks like, or how the database that we used as a reference was organized. So it's a database with 248 solutions that were defined through these fields here that we can see, like organization, for example, country, title of the solution, and so on. So the 248 solutions were presented by 234 organizations, and 48 countries participated and presented solutions to be added to this repository. The objective here was analyzing the content of the repository on deployable artificial intelligence and robotic solutions to draw conclusions on the potential applications of AI and robotics in this context. And the methodology, we analyzed the database using data processing and visualization methods. So simple statistic analysis was combined with more complex data processing to identify keywords per solution, and then mapping them using a network graph considering occurrence, co-occurrence, and a variable named class of solution. The analysis was then divided in two parts, as I mentioned before. The simple statistics, where we looked at the number of solutions per country and the distribution of the promoters, divided between public research institutions and private industry. And the second part, where we drew the network graph based on the keywords retrieved per solution, and then mapping the whole database. So here we see the first findings, focusing on the number of solutions presented per country. Here on the bottom, we see which kind of fields we will be using for each part or each step of the analysis. And we see that 48 countries in total presented the overall solutions. And most of the countries presented just one solution, but other countries like Spain and Germany presented a more elevated or higher number of solutions to the repository. Since this repository was also an European Commission initiative, we thought it could be interesting to see whether only European countries were participating, or if we would have also non-European countries proposing solutions here. And we found out that 194 solutions were presented by 26 European countries, so countries within the EU. And non-EU countries, we found that 22 countries presented as well 54 solutions. Then looking at the distribution between private industry and research institutions, we see that 211 solutions were proposed by the private industry, which is also an interesting finding from our point of view. Here is the dominant role of the private industry to propose solutions in this field, and also how close the European Commission appears in association with the private industry. And then also 37 research institutions, research institutions proposed also 37 solutions to this repository. Here we have just a summary of what I've been telling you. And we see that most of the countries have, for sure, clearly a higher number of solutions presented by the private industry. But we see also some exceptions, as for example, Greece, that has also a high level or a high percentage of solutions presented by research institutions, and Slovenia, just to name two examples. The second part of the analysis, we drew a network graph that had 3 steps. First, we needed to identify the keywords per solution. Secondly, we used 2 criteria or to variables to draw the network graph based on occurrence and co-occurrence of the keywords. And a third step was to identify the keywords or to link the keywords with a specific class of solution, which is translated by the sphere of implementation of the solution. And criteria and parameters. So to describe the solutions, we considered the fields that are here highlighted and used this text to retrieve then the text associated with these fields to retrieve the keywords according to these parameters. So each row in the database corresponds to one solution, and to be considered a keyword, the word had to be repeated at least 3 times within a solution and be longer than 2 letters, so excluding all prepositions, connectors, and so on. So doing this filtering. And we also did some grouping process in order to cover some abbreviations and that are in the end just definitions of the same concept. And here is an example of an output. For example, for the solution in row number 5, we find all these keywords. Data was repeated 14 times, health was repeated 7 times, authority 3 times, and so on. And here is the first output, the first network graph. So in total, we retrieved 241 keywords from the complete database, and we mapped the keywords in the network graph according to these 3 steps or 4 steps. Sorry, there's a mistake. So for step 1, the keywords were represented in the graph as nodes. The size of the node grows with the number of occurrences. So the highest occurrence means bigger bubbles. The edges are the links between keywords within the solution, within one solution, and then the strength of these edges binding keywords increases if the same combination is found in multiple solutions. These we call co-occurrence, which enable the visualization of clusters. And we already see here that some keywords are highlighted because they appear frequently in the database, like COVID, patients, robots, and so on. We will be coming back to this. So the last step of this analysis was to focus on this field in the database named class of solution, which was predetermined by the repository. So there were several categories that could be assigned to each solution, like diagnosis, disinfection and sterilization, law enforcement, and home delivery. We see here a sample of the database that some solutions were assigned more than one class of solution, but to this analysis, we decided to focus on the first category or class of solution assigned to them. So here we have already the attempt to assign keywords to a specific class of solution. And this was possible for most of them, but we also found out that some of the keywords were not strongly connected to a specific class of solution. And this we covered here. So where keywords like phone and masks were equally assigned or equally linked to several classes of solutions, and therefore we could not assign them to one of them particularly to move on to the graphic representation, and therefore we classified them as unspecific. So 97 keywords were in this category named unspecific. They are all here. And here we have then the second network graph with this new variable, the class of solution. And we can see that the graph displays the number of occurrences through size again, then co-occurrence through clustering, and the association with a class of solution through color. We see that again that some categories or some classes of solution appear connected with some specific keywords, and that diagnostics is the class of solution that appears as having a higher impact within the database. So most of the solutions proposed were linked to the problematic of diagnosing the disease. And this is the final finding that I will present today. So we see that, we know that the repository was looking at two specific topics. One was AI solutions and the other was robotics. And this was also mirrored in this analysis. So we find that there were two sort of clusters, one linking around robotics, which was specifically connected with a class of solution of disinfection and sterilization, and robots and robotics. So all the concepts around this word appear as quite some high occurrence. So we see that the bubble robots is quite present and evident. And the second cluster is around AI that we defined with data and other neighboring concepts such as models, machine learning, and prediction, and so on. So these keywords appear linked in a cluster and define the second big topic for the repository, which is AI. So these are just some findings and a short overview of the analysis we put together and we discuss in further detail in the paper. Thank you for your attention.
All right, thank you very much for this really interesting presentation. Do anyone have questions? I see we have a new panelist. Hello. A bit young, but that's good. You need to start early for ethics and that kind of questions. So if anyone has questions or comments, it is your moment. Nope. So I guess that this was a really clear presentation. Good job. I have one question. How did you do all this inference? How did you, because I know how you got the data set, obviously you explained that really well. How did you figure out how all this goes together? As a social scientist, I don't usually do that kind of statistics or any kind of methodology, basically methodology question. How did you get there?
The network graph.
Yes. All the graphs and all those things.
So there was some coding involved to retrieve the keywords, and after that the tools were just for visualization. It was nothing too complex after all.
This is replicable.
Yeah, yes, for sure.
Amazing.
Roxanne, I mean, there is so many students at our faculty right now that are seeking bachelor's thesis and stuff, right? So if any one of you that goes out to any of the IEAI researchers, right, would require some assistance in the form of a bachelor's thesis computer science guy, well, we could certainly try to arrange something, right? Just in case.
Caitlin
right?
and Professor Lütge are in right now listening in. So did you hear that? Maybe we can go there. That would be extremely interesting. Thank you very much.